We're now back for the final part of this example. The previous parts to this example will be linked in the description below of this video, including the assumptions that we're using for inflection points for portal frame method. I've cleaned things up a little bit, and what I've done is I've also added some information here. I'm calling this representation the axial and shear diagram, where I'm showing the maximum axial force and the max shear forces in kilonewtons. I've also added reactions here. Now, to be fair, if I wanted to be really picky, I'd remove the moments because it's not a reaction in kilonewtons. I won't be super picky, okay? So here, I'm going to do the maximum moments, internal moments, and reactions. So that's where I'm putting the moment reactions in kilonewton meters. I'm also choosing this direction as positive. So here's what's happening, okay? Like what we were doing for bending moment diagrams for frames, we have moments that develop here at corners, okay? And we have to show them properly. And like we learned in the previous video when we were doing these moment reactions, it's super easy and quick to do it as long as you have the shear for that member. Okay, so let's do it for columns. So we have these moment reactions here we got them previously. Refer to the previous video. Now we have to figure out the moment at this end here. So how do we do it? We take the shear corresponding to that end, 10, multiply it by the distance, 1.5. Okay, so that tells us that it's going to be 15. And the question is, what direction is it going to be in? If this moment, see, this force with respect to B is trying to cause a moment that is clockwise, the reaction here must be counterclockwise. Counterclockwise is the same as that. That means this is a positive moment. Make sense? I'm going to sketch it, but you don't have to, because otherwise things get busy, okay? So this here, like that. Okay? Okay. Let's do this column here. Okay? This column here, column CD. To find the moment at that end of CD, it's going to be this shear, not this shear, that shear, times that distance. Right? 20 times 2.5, which is 30. So this here is 30. Now, if this shear is causing a clockwise moment, the reaction here must be counterclockwise. So that means this here is a positive shear. So I'll just leave it like that, but that's what it means. It's a positive moment. Okay, let's do the moment at this end of the column. Are you seeing where I'm going with this? It is the shear 10 times 1.5, it's 15, and it's positive 15 because this reaction moment, this moment at this end of the column is going counterclockwise. Okay, so this is okay, not bad. Let's see if it works with the beams. We want to find what the moment is at this end here to make sure that it works with the beams. The shear in the beam is 6. With respect to this end, it's 6 up. 6 times half the distance, 2.5, right? That's 15. Okay, so that's interesting. Okay, now 15 going up like this is trying to cause a counterclockwise moment. That means at this end, you need a clockwise moment to balance it out. Clockwise is negative. So that's good, right? These two ends balance out. You have 0. Okay? So let's see what happens at this end of BD. Okay? We have a moment caused by this shear with respect to D. So it's 6 times 2.5. So it's going to be 15. Right? So that's at this end of BD. 15. What's the direction? Okay. This shear, with respect to D, it tries to go like this, counterclockwise. That means the reaction there has to be clockwise, which is negative. Interesting. Now let's look at this being dg. Let's look at the d end. Okay? So what do we do? For the moment, we use the shear. The shear here is 6. 6 times 2.5, what is it? 15. What direction is it in? Let's check. This 6, not that, this 6 with respect to d goes up. So it's trying to turn this counterclockwise. That means the reaction at this end must be clockwise. Clockwise is negative. So look what happens here. All of those moments balance out to 0. Good, we have equilibrium. Let's do this end. Do you already foresee what you should be getting as a value so everything balances out? This hopefully should turn out to be minus 15. Let's check. What we want here for the moment at this end is the shear times the half distance. So it's going to be this shear, not that, this shear, 6 down. 6 down times half the distance is 2.5. That's 15. That's promising. This moment wants to turn counterclockwise. That means that the reaction at this end has to be in the opposite direction, which is clockwise. With respect to that, clockwise is negative. And look at this. They now balance out to give you 0. So this is kind of like we've done with our shear bending moment diagrams. The shear diagram balances out to 0. We found that when we did G, right? Everything balanced out to 0. The bending moment diagram balances out to 0 everywhere. When you add up all the joints at corners and L's and T's, everything balances out to 0. So there you have it. The final result, we now also have the maximum moments. Okay? So the expectation then from a question like this would be ultimately to get this diagram with axial shear and reactions in kilonewtons, and this diagram with moments and reactions in kilonewton meters. And this should include positives, to say clockwise or counterclockwise, whichever one is positive. And here you don't need positives or negatives because you'll show the directions with your arrows. Now, this took quite a while, and I think we're up to 4 videos or so. But that's simply because I've taken the time now to work it out with you. If we were actually to solve this on our own time, on paper, it might take maybe 10 minutes. Okay? It's a very, very short question. Maybe even less once you get to be awesome at this. I'm going to do maybe a couple more videos, maybe solve a couple more examples, just to give you an impression on how they're done. But otherwise, practice makes you awesome. Okay? It's not difficult, but because it's new, it just takes a bit of practice. Thank you for your time.